Hello students. So now we'll see some of the long channel VI characteristics of a transistor. Okay. So we know that most transistors have three regions of operation: cutoff, linear region, saturation. Now let us derive a model relating the current and voltage for an NMOS transistor in each of these regions. The model assumes that the channel length is long channel, which is enough that the electric field is relatively low, which is no longer the case in nanometer devices. This model is variously known as long channel, ideal, first order, or Shockley's model. Now we know that the charge on each plate of a capacitor is what Q is equal to C into V. Okay, so the charge in the channel can be written as Q in the channel will be, because it acts as a capacitor, Cg into VGC minus VT, where Cg is what capacitance of the gate channel and VGC minus VT is the voltage which is attracting the charge to the channel. Okay, so the gate voltage is referenced to the channel which is not grounded. So VC will be the average of Vs in source voltage and the drain voltage, which is Vd plus Vs divided by 2. Now we can model the gate as a parallel plate capacitor with capacitance proportional to the area over thickness. Thickness is Tox. Okay, so Cg can be written as Kox epsilon naught Wl by Tox, which can also be written as Cox into W into L. Okay, where epsilon naught is the permittivity of the free space, that is 8.85 into 10 power minus 14. Then Kox is 3.9 times as great. Okay, so epsilon ox by Tox, sometimes it is we also term it as a Cox, that is capacitance per unit area of the gate oxide. Okay, so now each carrier in the channel, it is accelerated to an average velocity of v. Now this v is proportional to the lateral electric field, which is E. So the constant of a proportionality mu is called the mobility. So V is equal to mu into E. Mu is mobility, E is the electric field, V is the velocity, average velocity. The electric field E can also be written as VDS by L. Okay, so L is the channel length. Voltage difference between drain and source is VDS. Okay, so now based on that, the IDS, the current through the drain and source terminal of a transistors, can be written as Q channel divided by L into V. And if we substitute for Q channel and simplify, we get the value of IDS as beta into VGT minus VDS by 2 into VDS, where beta is what? Beta is mu Cox into W by L, and VGT is VGS minus VT. This describes the linear region of operation. This equation, whatever we have derived, it describes the linear region of operation. If VDS is more than VD saturation, the channel is no longer inverted in the and it is pinched off. So beyond this point, it is called the drain saturation voltage. So if you substitute VDS by VD saturation and simplify, and that will give you the IDS when transistor is in saturation. Linear VDS less than VD saturation. If VGS is less than VT, it is if VGS less than VT, what is that? Cutoff. Current is what? 0. And for linear region of operation, what is the current? Beta into VGT minus VDS by 2. Just now into VDS, we have just now derived. If you replace VDS by VD saturation and simplify, you get the value of IDS as beta by 2 into VGT the whole square. That is when VDS is more than VD saturation region. So basically 3 regions of operation. Cutoff, current is 0. Linear, beta into VGT minus VDS by 2 into VDS. Saturation, beta by 2 into VGT the whole square. So based on that, we have a problem wherein they have given you the values of WL, mu and Cox. You just have to substitute and find the value of beta. So this is the IV characteristics of an NMOS and PMOS transistors, long channel IV characteristics. According to the first order model, the current is zero for gate. The current is zero for gate voltages below VT. For higher gate voltages, current increases linearly with VDS. As VDS reaches the saturation point, VDS is equal to VGT. The current rolls off and eventually becomes independent of VDS. PMOS transistors also behave in the same way, but with the sign of all the voltages and currents reversed. Okay, the same thing is here. Okay, so that is the long channel IV characteristics. Now, when it comes to non-ideal IV effects, we have so many non-ideal IV effects. So, in long channel IV model, which neglects many effects that are important to device with channel lengths below 1 micron. This section uh, of the study of transistors when with channel length less than microns is called as what are the effects that we come across will be listed under non-ideal IV effects. In that, the first one is, we have so many non-ideal IV effects: velocity saturation, mobility degradation, channel length modulation, body effect, leakage, subthreshold region, temperature effects, and noise margin. So what is velocity saturation? So when the saturation current increases with increasing in VGS, velocity saturation and mobility degradation are two effects that causes the current to increase with VGS. So when carrier velocity is increasing linearly with field strength, we have velocity saturation. Okay, so V is equal to mu into E lateral, which can be written as mu into VDS by L. Similarly, we have mobility degradation. So from the equations we have derived, the carrier drift velocity and current is proportional to the electric field, E lateral, that is VDS by L, between source and drain. Okay. So now the long channel model assumes that the carrier mobility is independent of the applied field. At high voltage at the gate of the transistor, which attracts the carrier to the edge of the channel, which causes collision with oxide interface that slows the carriers, that is called as mobility degradation. The carrier approach a maximum velocity V saturation when high fields are applied, and this phenomenon is called as velocity saturation, and which causes collision with oxide interface and slows the carrier is called as mobility degradation. So the next non-ideal effects we have is channel length modulation, whereas ideally IDS is independent of VDS for a transistor, okay, in saturation, making the transistor a perfect current source. But the PN junctions between drain and the body forms a depletion region with a width that increases with VDB, as you can see in the diagram. The depletion region effectively, which shortens the channel length, L effective will be equal to L minus L dash, LD, you can call it as LD. Assuming VDS is approximately equal to VDS, increasing VDS decreases the channel length. As you increase the value of VDS, which decreases the effective length. So which shortens the length, results in high current, and thus IDS increases with VDS in saturation. So IDS is what in saturation, that is beta by 2 into VGT the whole square, but here it is 1 plus lambda into VDS. Increasing value of IDS can be written as IDS is equal to beta by 2 into VGT the whole square general. But when the channel length shortens, current increases, which is multiplied by 1 plus lambda into VDS. Similarly, we have the next parameter as body effect. Body is generally the common substrate in a MOS device, but when devices are arranged in series, this substrate voltage varies when VGS is more than VT. But if V substrate increases, the width of the depletion also increases. Therefore, the substrate should be applied such that it balances the structure and also the VT increase in VT. So this increase in VT with VS is called as body effect. Also, we have so many junctions, leakage currents, and transistor conduction, even when the transistor is in cutoff, substrate to diffusion junction, reverse biased. These some leakage currents are called as leakage. They're classified under leakage current. Subthreshold region, ideally at VGS less than VT, current should be zero. But most of the MOS devices will be partially conducting for gate voltages below threshold. and that is called a subthreshold region. Ideally, MOSFET should be off when VGS is less than VT, but but practically when you are using transistor, it even conducts when VGS less than VT, and that is called as subthreshold region. And these are some of the non-ideal effects of transistors.